Continue. And now is a good time to go over some terminology and vocabulary. This is our favorite stuff here. So when we're talking about sampling distributions, remember that can I change the what? The screen color? No, I think this is the proper screen color. Well, I don't want the keyboard. I will verify, but I'm pretty sure. Yeah, it's still disabled. So yeah, this is the proper screen color. You guys just got used to it and sad. All right. Okay. So we start off with a population. Now, I defined a population at the beginning of class. Does anyone remember what the population is? So we said we start off with a research question, and the population is everyone that is relevant to the research question, right? So this is everyone we wish we could study. Okay. And generally, the population has something called a parameter. Okay? A parameter is a property of the population. At the beginning of class, when I introduced this topic, I called it the quantity of interest. Okay, that would also be defined as our parameter. So in the examples that we did, I gave you the parameters, which was the proportion in the population that was left-handed, or the proportion in the population that were yellow pieces or orange pieces of candy. Okay. A lot of times the parameters are unknown to us. So usually, or maybe often, the parameters are unknown to us. And we wish to learn about the parameters by studying samples. Okay. I'll just say we wish to learn about the parameters here. Okay. Now, one method to learn about the parameter is through a census. Okay? And a census requires studying everyone in the population. Everyone . This is often very expensive and time-consuming, okay, and sometimes not possible. Very time-consuming. Time is money, so that makes it very expensive. And many times not practically possible. But thankfully, we don't have to take censuses, whatever. We don't have to take a census to answer a question. We can often answer questions about the parameter by studying a sample. Okay, so instead, a sample, which is just a selection from the population, that we can study. Ideally, what happened to my cursor? Oh, here we go. Okay. Ideally, the sample is representative of the population. And when we study a sample, a statistic is a numeric summary or a property, numeric summary or property of the sample. Okay, so populations have parameters, samples have statistics. Okay, and often these statistics are used to estimate the parameter. Okay? Often we use the sample statistic to make estimates about the population parameter. We got all this down? Okay. So when we do this process of using sample statistics to make estimates or conclusions about the parameters of a population, that is statistical inference. And I think on the very first day of class I asked, why do we bother studying statistics? And you guys remember what I said? I'm not surprised. I won't say I'm not hurt, but I'm not surprised. I'm just kidding. It's okay. So I said we study statistics because we want to make conclusions from limited data. Okay? Meaning that we can't take a census. It's too expensive to take a census, but we still want to know something about the parameter. So we take a sample, which is limited data. Based on our sample, we can make conclusions about the population. Okay. So again, so we have statistical inference, which is this. Yes. No. That's not what I want. It's the other class. Where are we? Stats XL10, May 12th. Slide 7. Here we are. Okay, we good? Okay. Statistical inference. The process of making conclusions about our population based on limited data provided by our samples. Okay. So just of note, in general, parameters often represented. No, let's just list these off. Okay, so we have parameters and the equivalent statistic. Okay, so we have the mean, population mean, mu, corresponds with sample mean, x bar. We have the population standard deviation, sigma, which corresponds to our sample standard deviation, s. And we have the population proportion, what symbol do we use there? P. And that corresponds to our sample proportion, p hat. We talked about getting a sampling distribution. Okay. So earlier we looked at the sampling distribution of p hat. Okay. So a sampling distribution is technically the distribution of all the possible values of a sample statistic. Okay? Which, you know, whether it's p hat or x bar or whatever it might be. Okay? It's the distribution of all possible values of a sample statistic. Okay? And in our previous problem, we said the standard deviation of the sampling distribution for p hat was equal to the square root of p times 1 minus p over n. Okay? This thing right here, standard deviation of the sampling distribution, this is also known as, also called the standard error. Which is abbreviated SE. Okay, so you will see this quite often, SE. And then, so instead of saying standard deviation of the sampling distribution for p hat, we might just say SE of p hat is equal to p times 1 minus p over n. Okay? because this is a little bit easier, or it's definitely shorter to write than this, but they're talking about the exact same thing. Are we good? No? Okay. I know. My hand is... What do they call that thing? Writer's cramp?
Carpal tunnel.
Carpal tunnel, that's like from typing too vigorously. Yeah, they got all sorts of things, right? Boulder's thumb and trigger finger if you're shooting, or most likely you're in construction and you're drilling things into the wall.
Don't you have one for gamers too now?
Yeah, any repetitive stress thing. Archers and pitchers. Well, pitchers, they're just destroying their shoulders, right? It's not. If you're good, you can make 10 million a year.
It pays off in that.
But you'll never be able to lift anything with your right arm at the end. Or left, Clayton Kershaw. Well, he's off to a rough start this year. Greinke's doing well. Okay, anyway. Dodger fans? Maybe, okay. Come on.
When they go to the World Series.
When they go to the World Series, oh yeah. Thanks, yeah, 1988, okay. Where did we go? Okay, so let's talk about getting quality samples, okay? So ideally, and I already mentioned this, ideally our sample is representative of the population. And I think I covered these topics also on the first day of class. But I'm going over them again now because it's an important concept, and something tells me you might not have remembered all of this stuff. So ideally our sample is representative of the population because we want to make conclusions about the population by looking at a sample, right? Ideally, the United Nations represents all the peoples of the world. Does it do that? Maybe, maybe not. It's done a fairly good job of preventing World War III, but it doesn't try to prevent all wars, and I don't know. Well, there's no. Anyway, okay. So ideally, our sample is representative of the population. Okay, if it is not representative, the sample is said to be biased. Now, in everyday language, biased generally carries this negative connotation of being kind of prejudiced or bigoted or, not being fair or just, okay? In statistics, it doesn't carry that, okay? It's a property of a sample that is not representative of the population. It is an undesirable property, but it doesn't come with all of this emotional and political baggage of saying this is biased against one way or another, okay? But we might say the media coverage of certain events are biased in that they are over giving too much coverage for one aspect and not the entire thing, in the idea that the coverage is not truly representative of the event. Okay, so we might say something like that. But a lot of times biased comes with this idea of some kind of political agenda or something like that. Statistics, we're not worried about, we're not concerned about those political stuff. It's just if the sample is not representative, it's biased, okay? And bias can come from all sorts of things, okay? So there's one so we have, the sample is said to be biased, and we can end up with a different kind of bias, okay? So we have non-response bias. Which comes from the fact that you go out and you take a survey and not everyone responds, right? Okay, you ask people a question or you send out surveys. I'll say that you send out surveys. And not everyone responds. Okay, that's going to cause non-response bias. Okay. You can have measurement bias, and there's all sorts of other reasons for causing measurement bias. But one of them is asking kind of poorly phrased questions, for lack of better terminology. Okay. Asking poorly phrased questions. Sorry, my handwriting is unclear here. So if you ask someone, I don't know, do you hate this and this, or do you, or you know, I don't know, do you hate America, or do you support, yeah, I don't know. Do you support increasing government spending in the military, or do you hate America, or something like that, right? It's like, are those my only two options? And you know, that would not give you accurate results in terms of the questions you're asking. Okay, so you got to make sure your questions are being fair if you're doing a survey. Okay. You can also end up with problems in the way you select people. Okay, so to select a sample that's representative, one method that should give representative samples is simple random sampling. Okay. And with simple random sampling, or SRS, we number every single person in the population. Okay, then we use a computer or some kind of tool. We use a random tool, generally a computer. to pick people one by one at random. And if you don't have a good tool, you can write everybody's name on a strip of paper, cut the little strips up, throw them into a hat, mix up the hat, and draw people out one by one. That is just about as good as random as you can get. You know, if you want, there are tools online. There is a website. Here, let me slide this over here. Called random.org. Okay. And if this works, I hope. Okay, and so you can just do something like free services. Where is the paid services? Free. Okay. List and strings. So you can just, like, if you got a list of people, list randomizer. All right. So you say, okay, I've got 6 friends. Joe. All right. Okay. Adam, Betty, Carl, Dave, Ed, and Frank. Okay, and I'm going to say, okay, well, I'm going to just pick one person out of this list, or maybe 2. So you just say, okay, randomize, and then we'll just say we're going to pick the first 2 people that show up in the random list. So you click randomize, and it goes, okay, and it picked out Adam and Ed. And so those are the 2 that get mixed up. Okay. Now, in the textbook, it talks about using a random list of numbers and doing things like that. I guess it might be useful to learn, but really, who's gonna? There's a random table in the back, and I can explain all. It turns out it's way too tedious. Okay, you want to do something truly random? Go to random.org, enter your things in here, boom. Okay, it's good. All right. If you've got this, you can do random lists and things like that. All right. And you've got the free ones, and you can apparently pay to have random things, and they explain how their random things are work, and it's based off of some weather satellite thing, and well, whatever. Because the weather is pretty much certain air phenomena can be considered random, and that's what it's based off of. I guess there's a question of what is truly random in the world, and that's like a metaphysical question. You know, a lot of times we consider the outcome of a coin flip to be random, but is it really random, right? Like, if we knew exactly how fast the coin left my thumb and how fast it was spinning and the properties, you know, how high it's going to go and how it's going to land, we might be able to predict exactly how it's going to land, right? So, is it random? I don't know. Okay, and you know, if are our brains just reacting to the chemical, whatever, reactions that are happening, the electronic things and the stimuli that we receive, and are the words that I'm saying right now, are they just already going to come out anyway because of the whatever? Okay, well, I don't know. I don't know the answer to this, right? I like to believe that such a thing as love exists, and it is my choice to. Anyway, okay. So, you know, I feel, right? So.
You think love is random?
No, I don't think that, okay? But maybe I don't know, okay. Yeah. Right, okay, anyway. This is not about that. We're talking getting representative samples from the population, which is a very important topic, okay? And so, so we have all of these things. And I don't know if you guys remembered, earlier today I said, when we were talking about the sampling distribution, there was a little star, right? And do you remember what that little star said? It said something along the lines of if certain conditions are met, right? If certain conditions are met, then the sampling distribution of p hat comes from the normal distribution. Sorry, my handwriting's getting worse and worse. But I said something like this earlier today, right? Good. I'm glad you guys are agreeing there. Okay, sorry, I will read this, and it says, if certain conditions are met, then the sampling distribution of p hat comes from the normal distribution. That's what it says in my chicken scratch. Okay, so if certain conditions are met. Now, this phenomena, statistical phenomena, that the sampling distribution of p hat comes from the normal distribution, that is known as the central limit theorem. So anytime somebody talks about such and such theorem, it's usually because it's a pretty big result, all right? So when we did that computer simulation and we showed that the little Reese's Pieces candies, the orange ones, end up looking like the normal distribution, somebody should have been like, oh my gosh, that's amazing. I would have never expected the normal distribution. I'm waiting for that to happen. Maybe it'll happen one day. But the fact that we get the normal distribution is a bit of a remarkable result, okay? So the central limit theorem is the idea that sampling distributions look like the normal distribution. Okay. Now there are conditions though, okay? Not just any old sampling distribution is going to look like the normal distribution. So there are a few conditions, okay? 3 conditions must be met in order for this normal distribution stuff to apply. Must be met. So I'll say all 3 conditions must be met if we want to use the normal distribution. Okay. And we do want to use the normal distribution. Otherwise, all of the questions would be unanswerable. We would just say, well, I don't know what the distribution is, so I can't answer your question. Now that might make your lives easier because that would just be a simple answer, and we'd just say, any question I ask on the test, you'd say, well, I don't know what the distribution looks like, so I can't answer your question. You might prefer that, but then nobody would bother studying statistics. We would never be able to make limited conclusions from limited data, and that would be very sad. Okay, anyway, our 3 conditions are that, number 1, the selected sample must be selected randomly. And each selection is independent of other selections. Okay, so we call this the random/independent condition. So somewhere in the problem statement, it should say your sample was selected randomly. And if it says that, you can assume that this condition is met. Does that make sense? Okay. And there are two other things. One is we don't want our sample to be too small, and we don't want our sample to be too big. Okay, so our sample cannot be too small. Okay, so this is known as the large sample condition. And this generally means we can expect, we either observe or expect at least 10 quote-unquote successes. This is an arbitrary label that we apply, and at least 10 quote-unquote failures. So the label success and failure, again, just means it is an arbitrary label, and what it really should be is we expect things to happen, whatever it is, to happen at least 10 times, and it also to not happen at least 10 times. So for example, when we were counting the orange pieces of candy out of our sample, we should at least expect either at least 10 orange pieces and at least 10 pieces that are not orange. So when we took samples of size 50, we said we expect 15 pieces to be orange, right? 15 is bigger than 10, so that's met. Okay? If 15 out of 50 are orange, how many will be not orange? 50 minus 15, 35. Okay? So we're expecting 15 to be orange, and we're expecting 35 not to be orange. Both of those numbers are bigger than 10, so this large sample condition is met. Okay? So to say 10 successes, another way is to say n times p should be greater than or equal to 10, and n times 1 minus p also has to be greater than or equal to 10. Okay, and so that's how we make sure our sample is not too small, or that our sample is large enough. So this is known as the large sample condition. I'll underline each of these. Okay. And then the last one is that the sample should not be too big. Relative to the population. Okay, so this is known as the big population condition. You rarely run into this problem unless you're dealing with a small institution or something like that. Okay? So basically, the population needs to be at least 10 times your sample size. Or another way to write this is the sample cannot be more than 10% of the population. Okay, these are both saying the exact same thing. Yes? Why isn't it always better to have a larger sample? That's a good question, okay? So imagine having a deck of cards, okay? When I pick that first card out of the deck, what's the probability that it's red? well, 1 out of 2, right? Half the cards are red, half the cards are black. So 26 red cards, 26 black cards, right? So after I draw out that first card, and if it's red, what do I have left in the deck? I have 25 red cards and 26 black cards. So technically, the next card I draw no longer has a 50% chance of being red, okay? Now, if I only draw one card out, it doesn't really affect it too much. It's still pretty close to 50%. But let's say I drew out 10 cards from the deck, okay? And let's say a bunch of these cards are red. Then what I have left is no longer very close to the original proportion of 50% red and 50% black. If all 10 of these cards happen to be red, I would only have 16 red cards and 26 black cards, okay? And so that actually messes with this condition of being independent. Each selection is independent of the other selections. When you take too large of a sample, what remains as being possibly selected no longer looks like the original population. So that's where you run into this problem. You can remedy this by doing something called sampling with replacement. So that would mean you take the card out of the deck and then you put it back in. So whenever you draw the sample, draw a card, you have always 52 cards in there. The only problem with that is you might select the same card twice, and then you have to decide, what do I do with that? Okay? So you can kind of avoid this by doing something called sampling with replacement, which is generally uncommon in practice, but it's valid as long as you have a rule for what to do when you select the same card twice or same person twice or something like that. Okay?
So why wouldn't you try to match the population instead?
So, okay, so the idea is we don't want to have to take a census, right? We don't want to take the entire population. So we want to take a sample.
But why don't you match the sample to the population? Like,
Well, so we don't, the point being we don't know what the population looks like, right? Let's say I wanted to know what percentage of the population, I don't know, owns a cat, okay? I don't know what percentage of the population owns a cat. So I'm going to have to select random people. Now, how can I select random people and say I'm going to get a representative sample of the population? You know, it's hard to say, right? I shouldn't go to Petco and survey people who go to Petco because that's going to give me, I'm going to get way too many cat people, right? That's going to be biased, okay? I also shouldn't go to, I don't know, the whatever allergy doctor who who prescribes, because then I'm going to get people who probably don't own cats as often, or I don't know, whatever, okay? Getting a truly random sample, it's a difficult thing to do, okay? So anyway, we have all of these conditions, so we should check to make sure these conditions are met before we do, as we get into it. So you're going to have a few problems, and then on the sample quiz, I'll put a few questions asking about, are all of these conditions met, or are any of them violated, or things like that, okay? Is that okay? All right. All right, so let's, we're going to do our first, this is our very first statistical inference, okay? Very exciting stuff now. Okay, so our very first statistical inference technique. Okay, so what is statistical inference again? I think I defined it earlier today, if you guys remember. The process of making conclusions about our population based on the limited data provided by our sample. Great, okay. And that's what we're going to do, okay? So when we did the problems, the sampling distribution problems, when I said if 15% of the population is left-handed, what's the probability that a random sample ends up 20% left-handed, okay? In that case, I said we knew that the population is 15% left-handed. Now, in general, we don't actually know what the population looks like, okay? So let's say we wanted to know our very important research question. Is what proportion of the population what's a good question to ask? What proportion of the population
Like Swedish fish.
like Swedish fish? All right, there we go. I know we have students from Sweden in here, right? Okay. Do you guys know what Swedish fish are?
But the ones you have is the real Swedish fish.
They are or not? They're
No.
terrible?
Yours are terrible.
Ours are terrible? Okay, so wait. So Sweden in Sweden, Swedish fish, are these like real candy things? These are not like just
Yeah.
Americans made up something and decided to call it Swedish fish,
But
like
it's just named fish.
like they're just
It's
called
not
fish?
Swedish fish.
When so what do you call it? Just regular old fish? Fish. Okay, so you have fish and you have
Fish candy.
fish candy. Okay. All right. So anyway, okay. So we'll say what proportion of okay, maybe we'll say of the U.S. population likes the U.S. version of Swedish fish. Okay. There we go. Okay. So what proportion of Americans like the American version of Swedish fish? Apparently, we don't know what's good for us. And for those of you who don't know, they're these little red gummy candy things, right? And I don't, huh? I think they're red, right?
They're red.
Generally, I mean, you can get other colored ones,
You're
but
talking about the sharp ones. Yeah, those are different.
okay. So, all right. So we take a survey, right? So let's we take a random survey. So there's your keyword there, random survey. So we know that our random survey condition or sample condition is met. Random survey. We ask, let's say we ask 140 people, do you like Swedish fish? Oh, we'll say 140 US people, okay? Do you like US Swedish fish? Okay. It's just like I saw a YouTube video where somebody took a bunch of fortune cookies, went to China, and was like, do you know what this is? And everyone's like, no, I have no idea what this is. And then they said, well, why don't you try it? And so they eat it, and they're like, oh, there's a piece of paper in here. It was quite entertaining to watch. That is kind of a terrible thing to put inside a cookie, right? Oh my gosh. Okay, so anyway. So out of 140 people, how many say yes? What do you think? 0? No, I like Swedish American.
72.
Okay, we will say 85 people say yes.
Maybe like 60 or something. 85 is
85 out of 140. I don't know. Okay, we're just making this up, all right? Don't get mad at me, all right? All right, you can be one of the no's. All right, so 85 people say yes, okay? What does this say about the general population of all Americans, right?
Yeah.
All Americans. Because that is our population in question, right? Do you guys have any Swedish fish? I would love to try.
Swedish candy, but not Swedish fish.
Okay, I would love to
I'll
try
take this,
real Real Swedish fish.
I think
Okay.
the person who proposed the question should get the can.
Okay. All right. We'll have a party. Not really. I can't. Okay. Okay, so what does this say about the general population of all Americans? Okay, well, let's, so this is basically our setup here, okay? We've taken a random sample. Based on our sample, we want to make a conclusion about the population. That's statistical inference here, okay? So, well, what do we know from our sample? So from our sample, so from our data, we have what? P hat, our sample proportion, is equal to 85 divided by 140, right? Our sample proportion is not 85 because a proportion is always between 0 and 1. So we do 85 divided by 140, and I get 0.607. Okay. So maybe I'll keep one more. 0.6071 of the population like Swedish fish, according to this. Okay. Does that mean that 60.71%, so 60.71% of our sample like Swedish fish? Does that mean 60.71% of all Americans like Swedish fish? No, not necessarily, right? Because when we took this random sample, because it's random, we might have selected more people that like Swedish fish, or we might have picked less people that like Swedish fish, or we might have picked just about the right number, okay? We don't know. We don't know. But if around 61% of my sample like Swedish fish, I would expect that for all Americans, about what percentage like Swedish fish? About 61% also, okay? Because what we learned from the sampling distribution is that if the population has proportion P, then our samples P hat come from the normal distribution, which means, for the most part, it stays close to P, and it doesn't go too far away. Yes?
So this is somewhat like the Reese's Pieces cup thing, right?
Yeah, except it's going backwards, okay? So in the Reese's Pieces thing, I said you know what is in the giant machine,
Right.
and we want to know what's the probability of getting this property of a cup. This time, we're looking at what happens in the cup, or the sample, and we're saying, based on what we see in the sample, what can we say about the giant machine? That's what we're saying here. Based on what we see in our sample of 140 people, what can we say about the population of all Americans? So we would expect the population to be somewhat close to this. Okay, we would be surprised if of all Americans, only 10% like Swedish fish, because that means something freaky happened with our sample. Okay? Or we would also be surprised if the answer was 100% of Americans like Swedish fish, because that means I got way too few people liking the American product over here. Okay? So we're going to create something called a confidence interval. So our very first statistical technique is called a confidence interval. Okay, and you've probably already seen something like this around election time. Okay, and the confidence interval basically says gives you the confidence interval looks like this: p hat plus or minus what we call a margin of error. Okay, so often around election time, it will say this many, the proportion of people who are voting for this candidate, candidate Jones for governor or whatever, they'll say candidate Jones is leading 52% with a 2% margin of error or something like that. Okay? So we're going to say the population proportion P, here, let me say that, write this. Population proportion P is between P hat minus, I'm going to just abbreviate the margin of error, and P hat plus the margin of error. Okay? And we can say, and we are I'm going to just start off with saying 95% confident about this statement. So I'm just doing something very quick. Don't mind me for a second. Okay, so for example, in this problem, I'm going to just say, let's say we end up with an 8% margin of error. Okay, so I'm going to just say we have I'm going to just say 607 plus or minus an 8% margin of error.
Did you just make that number up?
I didn't just make it up, but just for now, let's pretend I did. Okay? And I will explain how we get the margin of error in a moment. But I want us to understand how we even use the confidence interval in the first place, because that's the important part. Calculating it is secondary. It's still important. You've got to learn how to calculate it. But how to use the confidence interval, that's the important part. Okay, so I'm going to just flip to the next slide. Is everyone okay with that? And we're going to just say, let's say our confidence interval is 0.607. Okay, because we're making confidence interval for P. Our sample ends up, so let me just copy this. And just cut this out. So remember, this comes from our data, okay? So this serves as our estimate, okay? Our estimate of P based on our sample. And that should make intuitive sense, because what we're saying is that, you know, what proportion of all Americans like Swedish fish? Well, we don't know the answer to that. So we surveyed a bunch of people, and in our survey, around 61%, 60.7% liked Swedish fish. So right now, if we had to make a guess for the percentage of all Americans that like Swedish fish, our best guess would be around 60.7%. Okay? But we've got to give ourselves some breathing room. And I'm telling you the margin of error is 8%. Okay? So our resulting confidence interval will then be 0.607 minus 0.08, which gives me, I think, 0.527. But I'll just double check. Yeah, 0.527 and 0.607 plus 0.08, 0.687. Okay. So I'm going to just write our 95% confidence interval goes from 0.527 to 0.687.
Where do you get 95%?
Again, I will cover all of this, but just for now, just go with me saying 95%, okay? And I'll talk about what it means to be 95% confident and all of this, okay? So right now, we would say something along the lines of, based on my sample, based on my sample, I am 95% confident that the proportion of all Americans that like Swedish fish is between 0.527 and 0.687. Okay? So we're saying I'm 95% confident that the proportion of all Americans that like Swedish fish is between basically 53% and 69%. Okay? Does that feel okay to say? Okay. What does it mean to be 95% confident? Okay, it means we're pretty confident, but we're also kind of making a disclaimer saying, I could also be wrong. And I'm 95% confident in my answer, but I'm also 5% unsure about it. and that's because we don't know what the population looks like, okay? Could the population actually be only 51% like Swedish fish? Yeah, that's possible. And that would mean we just happen to get a slightly weird sample where more than, where 61% like Swedish fish. And that would be considered unusual, but that could happen, okay? So we don't want to guarantee that the proportion in the population is between these two numbers, because we can't guarantee that. We can say, based on what we understand about statistics, I'm pretty sure, I'm 95% confident that the population proportion is between these two numbers, but I can't promise that. I'm only 95% sure about it. If I wanted to be more sure, if I wanted to be 99% confident about my answer, what should I do to my interval? Would my interval get even bigger, or would it get even more smaller? It would get bigger, right? If I want to be more confident that P is between the ends of my interval, I would say I'm 99% confident that P, the percentage that like Swedish fish, is between 40% and 90% or something like that, okay? If I want to be 100% confident, what would I have to say? It would be between 0 and 100%. That's the only way I could be 100% confident. But it's pretty useless to say, oh, I'm 100% confident it's between 0 and 100%. That's like being a smartass, right? What percentage of people are going to vote for whoever, the Democratic candidate in the 2016 election? Oh, I know the answer. It's going to be between 0 and 100%. People say, like, go away, you're stupid, okay? Not stupid, you're not wrong, but you're just annoying me, okay? So we have to trade off, if nobody wants a 100% confidence interval if it's going to be useless, okay? So you just say, okay, well, I'm not 100% confident, I'm only 95% confident, but I can give you this range here, okay? And we can, in fact, decrease our confidence more and more and create a smaller and smaller interval at the expense of confidence, okay? So we could make a smaller interval, but we might only be 80% confident about our answer, and that means there's a pretty good chance that we're wrong, okay? So that's what it means, okay? And notice I'm saying confident, and I'm not saying a 95% probability, okay? Because probability implies an uncertain outcome, something that's not yet determined. Okay? But if we think about the population, there's nothing uncertain about it. There's a certain proportion in the population that likes Swedish fish, and that's not an uncertain number. We don't know what it is, but there's no uncertainty in that number itself. So we just talk about being confident. Okay, so how did I get this 0.08, okay, or whatever number we're talking about? Okay, so let's talk about the creating the confidence interval itself. Okay, so study this, and especially this statement. This is important. And I'll try to put some question like this on a sample quiz. I'm going to try really hard to make a sample quiz for you guys, because I know it's helpful. I don't know if it's making the class too easy though. You know, I'm like, of course you guys would say that.
You need an easy class. Too many classes that you're teaching.
Oh, it's a lot of work to make the class. Make the class not easy, but make the class fair, but also where I feel like you guys are learning and challenging enough where I feel like you're learning. Okay, anyway. So making the confidence interval itself. We said the confidence interval is p hat plus or minus the margin of error. Okay? The margin of error is equal to, so I'm going to just rewrite this as p hat plus or minus, I'm going to call it z star times the standard error. Okay, so the z star is just a single number. And I'm going to further break down the standard error here. Okay, so for a confidence interval, the standard error is equal to the square root of p hat times 1 minus p hat over n. Okay? Notice this is very similar to the standard error for the sampling distribution, but the key distinction here is that we're using p hats. Okay? So this is very similar. To the standard error in a sampling distribution, but we use p hat here, okay? And this is for a confidence interval where we use the p hats, okay? Make sure you don't get them mixed up, because you're going to get the wrong answer if you get them mixed up. So what do we do about this z star? Okay, so these are just numbers you must memorize or make sure you write on your note card. Okay, if you show up next week and you don't have these numbers memorized or on your note card, I'm just going to say, sorry, I warned you. Okay, so it depends on the confidence level and the corresponding z star. So you can make an 80% confidence interval, you can make a 90% confidence interval, a 95% confidence interval, a 99% confidence interval. Technically, you can make any level confidence interval you want, but these are probably the most common choices. Okay. Could you make a 93% confidence interval? Sure. Does anyone do that? Not really. Okay. It's like, could somebody set the speed limit on the street to be 37 miles per hour? Yes, but I mean, what city would do that, right? Okay. So the numbers associated here, 1.28, 1.645, 1.96, 2.58. Okay. So either memorize these or make sure they're on your note card. Okay? Now if you look these up in your Z table, you would see that 1.96 actually corresponds to 97.5%. and 1.645 corresponds to 95%. It's because you're going to both the plus and the minus, and you're getting the area in between, and that gives you this. Okay, if that made sense, great. If it didn't, don't worry about it. These are just the numbers you need to know. Okay, so let's do, with our last 7 minutes, let's make another confidence interval. Okay, so you survey. Your next most important research question, okay, what percentage of Americans like Carl's Jr.? Who likes Carl's Jr.? I don't know. Okay. So he just asked you a question. Do you like Carl's Jr., yes or no? No, you know, we're not going to say, do you like Carl's Jr. over such and such? We're just going to say, what percentage of Americans like Carl's Jr.? Do you like it or not? Okay? I don't know. What? So let's say, so we survey, let's say 200 random Americans. Okay, out of those 200 people, how many say yes? So the vegetarians will say no. Who else says no? I don't know. Okay, vegans and vegetarians. Okay, so what percentage of people do you think like Carl's Jr.? Actually, and it's like what east of the Mississippi, it's Hardee's. Did you guys know this? Yeah. Yeah. Okay. Carl's Jr. / Hardee's. Okay.
Wyoming too.
Okay, so maybe east of the Rockies. Who knows? Okay. Some parts of the U.S. it's Hardee's, and some parts it's Carl's Jr. Okay. Okay. So out of 200, how many say yes? What, just give me a number. Okay, 120 people say yes. Oh, our numbers are going to be too similar to the other problem, but whatever. Okay. So I'm going to say make a 90% confidence interval for the proportion of all Americans that like Carl's Jr. Do they have Carl's Jr. in other countries?
In Lebanon, it's Hardee's also.
They have it in Lebanon. Okay. So the answer is yes, they do have it in other countries. What percentage of Lebanese like Hardee's? I don't know. I wonder, you know, do they like bacon in Lebanon? Is that? Yeah. Okay. I don't know. I don't know anything about Lebanon, and you know, other countries they have. You know, like they brought McDonald's to India, but they don't sell beef hamburgers. They sell, I think, sheep. I don't know. Something. McDonald's is the #1 consumer of sesame seeds in the United States for their buns. Okay.
Fun fact of the day.
Yeah. Where do I learn all this? I don't know. I read too much junk. Okay. All right. Okay, we got 3 minutes left, so I better just do this problem for you guys. Okay, so just pay attention. So we're going to start off, and we're going to check p hat. P hat is what? 120 divided by 200, I get 0.6. So that's my p hat, okay? I'm making a 90% confidence interval, so what z star do I use? Z star is going to be 1.645. What is my standard error? I'm going to use p hat 0.6 times 1 minus 0.6 divided by 200. Oh, and I'm forgetting to teach one thing, so I have to. Oh gosh. Okay. 1 minus 0.6 divided by 200. We take the square root of this. I get 0.0346. Okay, and I'm going to multiply that by 1.645. So my margin of error, when I multiply this and that together, I get 0.057. Is that okay? 0.05698. I'm going to just round off to 0.057. So my confidence interval is going to be 0.6 plus or minus 0.057. So that goes, so I do 0.6 minus this, and I get 0.543 to 0.657. And I make a statement like, I am 90% confident that between 54.3% and 65.7% of all Americans like Carl's Jr. / Hardee's. Is that okay? So write that down. If somebody asked you this question then, and someone said, I think 70% of Americans like Carl's Jr. or Hardee's. I think 70% of Americans like Carl's Jr. Would you say you might be right? Or I mean, would you say I have evidence against that? Or would you say I don't have evidence against that? Somebody says 70% of Americans like Carl's Jr. Okay, so, all right. So someone, someone says, so if we're asking about 70%, we look at our interval and we see we're 90% that the percentage of Americans that like Carl's Jr., we're 90% confident that that percentage is between 54.3 and 65.7%. So 70% is outside of that range. So we're pretty confident that 70% is not the true proportion. Okay? So we can say something like 70% is not within our interval, within the interval. So we have evidence that the percentage of Americans, and I'm running out of space here, let me see if I can slide everything up. That the percentage of Americans who like Carl's Jr. is not 70%. Does that make sense? Okay. And on the other hand, if somebody says, I think 63% of Americans like Carl's Jr. Do we have evidence against that? No. Okay. Because 63% is within our interval. Okay. And so any value that's within our interval seems like a plausible and reasonable answer. Okay? It doesn't prove that it's 63%, but we don't have evidence against that.
Since we're only 90% sure,
Yeah, we're only 90% sure. So,
is 70 too much out of the range?
we just say, we're 90% sure that it's not 70%, okay? We can say that, okay? We can say something like that. Or we can even increase the thing
Yeah.
to something a little higher, but